All right, let's go ahead and get started. We are ready to continue our discussion on capacitors. I can tell it's a almost rainy day outside. Very few people in here. Hopefully they'll catch up online. We were talking about last time what the capacitance of a parallel plate capacitor was, and we said that the capacitance of a parallel plate capacitor was epsilon naught A over D. Again, it only comes down to the geometry, not what the charge or voltage is on or across the capacitor at any given time. So if that's what we're concerned about, if you up the voltage across a capacitor, what do you expect to happen in response? It drops, yeah. If you up the voltage, you would expect the charge to increase across the capacitor. So we've got this nice linear relationship that as the voltage increases, the charge across the capacitors also have to increase such that the capacitance stays more or less the same. So another one, you can go through and look at your book's derivation of this capacitance, but it is conceivable, not inconceivable if you're a fan of The Princess Bride, it is conceivable that you could take two cylinders and have one outside the other in the shape of two cylinders. And when you do so, there is a certain amount of capacitance that would be associated with that system, where on the inner wall, the inner capacitor, the inner conductor, you have charge plus Q. On the outer wall, you have charge minus Q. And from that, you can go through your book's derivation, or you can trust me on this, check it out later if you want to, that the capacitance of a cylindrical capacitor is 2 pi epsilon naught L, where L is the length of the capacitor, divided by the log of R2 over R1. Log of R2 over R1. And so the relationship is still epsilon naught A times D, but that's kind of obscured here a little bit, right? I mean, it depends on the area. Well, that's where our pi and L come from. And then we've got divided by the ratio, the log of the ratio between the inner and outer radius. So as you separate these further and further away from one another, as R2 gets bigger and bigger and bigger, then you have to consider that the logarithm does not have an asymptote, but it does flatten out very quickly. That you have to have these two things very close together in order to have a natural log that is close to 1, in which case you would end up having, you would end up having a higher capacitance as you bring these two cylinders closer together. How is the capacitance affected if the potential across a cylindrical capacitor is increased from 20 to 80 volts? How is the capacitance affected? All right, so we would expect that the capacitance stays the same. We're not changing the geometry when we change the potential, the voltage. So what changes here is that if we're increasing the potential, the charge has to increase. But overall, you would expect the capacitance to stay the same. If it was 1 microfarad before the increase, then it should be 1 microfarad of capacitance after the increase. So how is the stored charge affected? Well, I just answered this, but I guess we'll make sure that you're paying attention. Yeah, so as you increase potential across a capacitor of any geometry, cylindrical, spherical, wound up as a double helix or something like that, the increase in voltage corresponds to an increase in charge stored. You can see that from, for example, if you write out the equation, we said that capacitance, at least the equation for capacitance, is Q per volt. And if this stays the same, then if voltage increases, charge has to increase. Or maybe an easier way to see that is multiply by V on both sides. You get C times V equals the charge on each capacitor. So if this is constant, it stays the same, but this increases, then that's going to correspond also to an increase in the charge stored on the capacitor as well. So increase the voltage, increase the charge. Basic rule of thumb on any given capacitor. And with that, if you imagine what happens when we connect a capacitor to a power supply, let's say a 20-volt battery, since that's what we were talking about before, then what happens is, if you imagine this on the atomic molecular level, then what I'm doing is I'm sending charge along one branch of the circuit, and I pop one electron onto one plate, and that's going to draw or push an electron away on the adjacent plate. I pop another electron on, I pop another electron on, and I keep popping electrons on until I can put no more electrons onto that plate for the given capacitance and voltage. Well, what's happening is I'm putting a lot of negative charge on one plate, I'm putting a lot of positive charge on the other plate, and what ends up happening is that I have forced these electrons to be in an area where they themselves are repelled by one another. And so in doing so, I have stored energy in my system. The way that I do that is you can recall that the change in potential energy from a charge is equal to the potential times the differential change in the charge. And potential is Q over C on a capacitor, so charge per capacitance. And therefore, you can take the integral and you end up getting that the potential energy stored on a capacitor goes as 1/2 Q squared over C, or using the relationship between Q, C, and V, you can say that the electrical potential energy is 1/2 Q squared over C, 1/2 QV, or 1/2 CV squared. So, depending on what you know about the capacitor, whether it's the charge on the capacitor, the voltage across the capacitor, the capacitance itself, then this is how you would measure how much energy. In a lab, it's really hard to measure charge. One thing that's really easy to measure is that you know the capacitance within tolerance based on what you just pulled off the rack, or you know the voltage across it using a potentiometer. And so in the lab, the most practical way to measure potential energy or energy stored on a capacitor is 1/2 CV squared. So as you increase the voltage, you get a parabolic increase on the energy stored on the capacitor. Okay? Any questions so far? Okay. A 200 microfarad capacitor is charged to 200 volt. How much energy is stored on the capacitor? Good. I would have 200 volts squared, so that would be what, 40,000, times 200 times 10 to the minus 6, so that would give me 8, but then I have to multiply by my power of 1/2, and that's where I get 4 joules of energy stored on the capacitor here, which if you think about it, knowing how much energy, say, a moving electron has with some reasonable speed, 4 joules of energy is a lot of energy stored into some sort of capacitor there. So, since a charged capacitor has a potential between, or I should say across the conductors, there's an associated electric field. And your book uses the parallel plate capacitor to derive the energy stored in the electric field to be U is equal to 1/2 epsilon naught times E squared times A times D. The interesting thing about this is that they use this kind of, if you take electromagnetic theory, when you, as you go further in your career, the interesting thing about this statement is always true, regardless of where the electric field comes from. It does not have to be the electric field between the plates of a parallel plate capacitor. What I'm saying is, if you want to know the energy stored in an electric field, then you end up getting 1/2 epsilon naught E squared times the volume that the electric field exists in. Or rather, you would end up having to integrate over that volume because you don't expect necessarily that the electric field is constant in that volume. If there is an electric field present, ultimately we talked about that means that there exists somewhere in the universe an imbalance of charge. Right? Because electric field lines come from positive charges and they terminate on negative charges. So if an electric field exists, then that means that they're coming from positive charge going to negative charge, and that is imbalanced somewhere for the electric field to exist in that region. What this helps us do is, if you know what the electric field looks like, now we have a way to calculate how much energy is associated with that electric field. And the more useful term that we end up using a lot in electromagnetic theory is the corresponding energy density, where we divide by the volume, and the energy density within an electric field comes out to be just 1/2 epsilon naught E squared. You want to know how much energy is stored in any sort of electrical configuration? 1/2 epsilon naught times E squared will get you most of the way there. Just love it when you can kind of pull things out of thin air in an intro physics class, and then it turns out that with this very specific geometry and setup, you end up getting what is true in every general case. The energy density in an electric field is 1/2 epsilon naught E squared. Pretty cool. All right. No, we're not going to do problems yet, but how you doing? Out of curiosity, and I'll see if there are any questions here in just a second too. I got to thank AI for the little funny ways to answer this question. Your brain is short-circuiting. I'm sorry. I'm assuming that's partially my class's fault, but not just my class's fault. Mostly just the weather? If your brain is short-circuiting in bad weather, be careful of being struck by lightning. That's all I got to say. Like, some sort of charge buildup, you're going to walk outside, don't get struck by lightning. It's a bad day. Do what? It is kind of nice outside. Just, if you're nearby a villager, just be careful if they get struck by lightning, because then they might turn into like a zombie villager. Or, into a, what? Yeah, a witch, thank you. Yes. They have to get attacked by a zombie. Are there any specific questions about capacitors before we dive in? Now that I upgraded my Menti subscription when my old one expired, I got the ability to moderate. So no more crazy questions that just randomly pop up on the screen. Is the chapter 24 homework still due today? Yes, it's still due today. I could potentially, because we're talking about capacitors today. We're going to finish talking about capacitors. This came from the fact that Last semester, there was feedback that said, hey, I didn't like that the last chapter's homework was due the night before the exam. I didn't feel like I could study, so I'm fine pushing it back till at least tomorrow night, if that would help you guys. Okay, I'll push it back to tomorrow night. Somebody send me, not all of you, somebody I elect Maggie, send me a Canvas message to remind me to push back the due date. Okay, that's answered. What is momentum? That's an excellent question. Momentum, we have no idea what momentum is. Hello, thank you. Will the formulas be on the exam next week? Yes, that equation sheet that you can find in the Module 1, Unit 1 module on Canvas, you'll find that equation sheet. That'll be exactly what you have on the exam next week. So yes, please be aware. I did tell you something that was incorrect. I have decided to let y'all write on your exams this time. And instead of having to print two different things, send two different things to the copy center, I'm going to have your equation sheet stapled to the back of your exam. You can rip that off if you want to. I want everything back at the end just so that way I can figure things out if clickers go wrong. But yes, your equation sheet will be stapled to the back. You may rip off the equation sheet. I'll remind you that afterwards. Yes, Friday, thank you. I appreciate that feedback. Can you go over deriving expressions for capacitors? I don't know, for whatever this question was, can you go over deriving? I'm not sure exactly what you mean by that. Would anybody like to enlighten me a little bit? Yes. Oh, having a nice concept map? Probably what would happen is we would want to look at instead just expanding onto our previous concept map. But maybe I need to publish that to Canvas, and I'll try to add a few things before I do that. Is systems of capacitors on the test? Yes. Systems of capacitors, in fact, that's what we're about to do right now. What would you suggest studying specifically for the exam? I would recommend studying, going through, if you look, there are conceptual questions at the end of each chapter. That's a good place to start to make sure that you understand how to do the first 24 problems on your exam. After that, look at example problems in the text of your book. And then if you still have time or want to continue studying, look at the problems at the end of each chapter in your book. In terms of what sections will be on the exam, that's also a good question. Let's see here. What sections will be on the exam? If you pull up our tentative calendar, we did get through all of this, so if you look at this column right here, these are the sections that will be on the exam. For example, I think we left out a section in chapter 23 and maybe 22 as well. So be aware that these are the sections that are on the exam. Those are going to be the ones you want to focus on. Chapter 21 through 24, knowing that we skipped a few sections in a few of those chapters. But yes, this exam will be over chapters 21 through 24. Yep. You can take a picture of that if you want to, or it's on Canvas if you want to look that up as well in the Unit 1 at the beginning of the course overview module. Yeah. Okay, that's a good question. Does 1/2 CV squared equal 1/2 E epsilon naught E squared? Only within the confines of a parallel plate capacitor. Within that, I should say, 1 half CV squared would be equal to this times the volume of the space between the plates of the capacitor. So you'd end up having to multiply times A times D to get this statement to be true between the plates of a parallel plate capacitor.
So with this equation, you were given the volume, you can find the electric field, right?
If you were given this equation, you could find the electric field. Yeah, I mean, if you're within the plates of a parallel plate capacitor, then you would end up having 1 half CV, this is voltage, squared, is equal to 1 half epsilon naught E squared times volume. I'll use little v there. So you could find the electric field if you already know the potential stored across. The 1/2s cancel out. If you know the capacitance and the voltage, you could solve for E is equal to CV squared over epsilon naught volume square root, right? So you could do it that way if you wanted to. That's one of the more complicated ways that I would solve for the electric field within a parallel plate capacitor. If it's within a parallel plate capacitor, we said that electric fields were equal to change in voltage over change in distance. Let's call that X, right? So the easier way to do it, since really we actually said that that was a derivative, right? But if the change is constant with respect to the change in X, that's where you can say that the voltage across the plates divided by the distance between the plates, that would be the easier way. You know that there's 10 volts across the plates, and you know the plate separation is 2 millimeters. Well, there you go. You know the electric field is going to be 10 volts divided by 0.002 meters. That would be an easier way to do it. Another question that just popped up, is there going to be a review? I don't know where that one went. Is there going to be any type of review we will have, or do we need to work problems from the book? My general rule of thumb is start with what you know. Start with I won't publish any extra problems. You've got all the problems that we've done in class and the problems we missed on Canvas. So I won't work these specifically because they're going to be the ones on the exam. I want you to be able to extend a little bit upon what you know. So I don't publish any extra problems or solutions, but if you start with the problems we did in class and try them by yourself, that's an excellent way to review. Then, I mean, you got to think, I chose the problems. That means I liked them and felt like they were a good summary of what you can expect to see on the exam. Then go to the example problems in your book. Then go to the problems at the end of each chapter in your book. The stuff we went over in class? Yes. Yeah, if you go to our homepage in Canvas, first off, if you go to the course overview tab right here, you've got the syllabus and that tentative schedule. You can see day by day what we've covered. After that, you can go down to Unit 1. You've got every slide deck that we've used so far. You've got every example problem without the solution. You've got every example problem that I've done in class with the solution, including the ones that I missed too. And then the equation sheet that I keep talking about is right here as well. And then, of course, all of our lectures are recorded on Panopto. So, yeah, no problem. Yes?
With the examples, do you mean like inside of the chapter, there's examples? And
Yeah.
at the end, there's also more examples?
Yeah, within each section, there's on average about 2 example problems where they give you a problem statement. I recommend solving it without their solution. They have a solution there. Try it yourself without it. But yeah, per section, there's about 2 example problems, especially if it's a problem-heavy chapter or section, then you'll might get a few more example problems. Then you go to the end of each chapter. Here's another good thing to review as well in terms of concepts. And I know even when I was a student, we had already shifted away from the generation of reading textbooks, but at the end of each chapter in your textbook is a chapter summary. It goes through like major idea, but by major idea, tells you what that major idea is, tells you the associated equation with it. Boom. After that, you get about on the order of 20 conceptual questions before you start the new chapter. Those are good to study for the first 24 questions that I'll ask on the exam. Then you get an additional 60 to 80 problems. That's where I pull most of the problems that we do in class, so you might recognize some of them. But you think, I do about 3 problems per section. Well, with there being 80 problems, that means that there are at least 60 problems that I didn't hit at the end of each chapter. They're listed with 1, 2, or 3 dots. 1 is easy, 2 is intermediate, 3 is difficult. Your exam questions will be in that 1 dot to 2 dot range. So make...
Conceptual ones, should we expect the stuff that's in our text to be what's going to be on the test?
Oh, yeah. I mean, I have built the lectures that I give based off of the text in your book. Yeah, I mean, physics doesn't change, but I try to make it as simple, like, if I'm going to make you purchase or do the Charger course pack for a particular... I know, but to your benefit, I want it to line up as best as it can. So, I mean, yeah, I want it to line up for you. So, yes, you'll find that my lectures should be very similar to what's in the book. Okay, let's move on. We're done with this one. Let's go ahead before we start problems. We're going to actually dive in here first and just go ahead and knock out all remaining lecture content. Present. Any other questions while y'all are logging into this new Menti deck?
Are we going to get our test back now that we
Still torn on that. Mostly because I don't want there to be a repository in 5 years of here's all of Waldron's tests, and you know he's going to do this one. That's my biggest hesitancy towards passing back exams. So it'll probably be the same thing where you're welcome to come back and look at in my office at exams, but I don't know that I'll be passing them back because I would like to reuse a few questions here and there, and I wouldn't like you students just to memorize my exams instead of trying to learn the material. Okay. So there are 24 conceptual multiple choice questions worth 2.5 points apiece, summing to 60 points. There are 10 numerical questions that are 4 points apiece, summing to 40 points. So 60% of your grade will be the theoretical questions, 40% of your grade on the exam will be the numerical questions. Yep. If you didn't have me last semester, just look for someone in this class who looks like they kind of know what they're doing and ask them what my exams were like. It's very similar to the one that I gave you on Tuesday, right? I mean, some of those questions, as a matter of fact, were ones that I used on the exam for this class last semester. So it gives you an idea of the difficulty. All right. So if we want to look at systems of capacitors and power supplies, meaning if we put multiple capacitors together in the same circuit, how do we expect that set of capacitors to respond? Well, what ends up happening if you have capacitors in parallel, then I would expect the voltage drop across capacitor 1 here. Let's say I go from 10 volts to 0 volts. I get a 10-volt drop across this capacitor. I have to have a 10-volt drop across the adjacent capacitor in parallel, right? You can imagine, if you're not familiar with looking at schematics or circuit diagrams, whatever you want to call it, that if we're working with ideal conductors, then I get 0 voltage drop across any one of these black lines here. So 0 voltage drop across the black line, that means that I've got this whole black line right here is equal to V sub A. Call it 10 volts. And this other additional black line here is going to be at 0 volts, V sub B. So regardless of how I go across from one black line to the other, I get the same voltage drop. For capacitors in parallel, we expect that the voltage drop across those capacitors to be uniform. If I go from A to B from one, I go from A to B across the other. 10-volt drop. And the way we would draw that more specifically, instead of drawing a parallel plate capacitor, the symbol that we would use in a circuit diagram or schematic is going to be those two parallel lines representing two different capacitors. And in that case, when you have capacitors added in parallel, what we expect to find is that the capacitances add together. At this point, when I didn't have Menti question moderation, I got a question last semester because I kept saying capacitances. They said, what's the plural of capacitance? I would expect it to be capacitae. I don't know. I have no idea. I'm not a grammarist. I didn't do well in grammar school. That's why I chose physics instead. Capacitances in parallel add together. So for capacitors in parallel, the equivalent capacitance should always be greater, equal, less than. Oh, okay, good. I'm glad. Sometimes that happens when I reset. I don't know why. So that means it's going to be shown on all the slides. So you'll get the answers ahead of time. Woohoo! Capacitors in series are those that have common charges. The way you can imagine this is imagine that we're connected to some power supply, and it's going to pop on here, I don't know, let's say 1 microcoulomb of positive charge, which in turn is going to draw up 1 negative microcoulomb of charge onto this plate. Well, that charge had to come from somewhere. As far as we discussed on the first day of class, there's such thing as conservation of charge, so I don't expect charge to come from nowhere. Okay, if that's the case, then I've got here that there has to be 1 positive microcoulomb of charge that was left in excess on this plate, this top plate on the second capacitor, and that's going to drop when, well, you can kind of see the stacking effect that we get here. If we pop on 1 positive microcoulomb of charge, there has to be an associated negative microcoulomb of charge, et cetera, et cetera. You can go through and show, and your book does show, that the capacitances add in inverse to give you the inverse capacitance for the capacitors in series. Right? If you know that each one of these are 1 microfarad capacitor, then I have to add 1 over 1 added together. So that would end up being 1 over 1 plus 1 over 1. That's 2. But then I have to take the inverse of 2. So I go from 1 microfarad capacitors, if they're both 1 microfarad capacitors, to having 1/2 microfarad capacitance. Now, in my algebra-based physics class at Harding, what would end up happening is I'd always get one of them to say, I don't know why this is useful at all. To them, most of them were pre-med majors. If you know the capacitance of different organs in the body, or different molecules in the body, or different cells in the body, you can add them up, and usually there was some way you could think of them as being in series or parallel, and it would allow you to figure out what the capacitance of the system could be. For electrical engineers, you know that all you have in your shop is 1 microfarad capacitors. Well, adding them in series or parallel in enough different configurations, you can come up with any capacitance that you want to. You know, based off of your design, that you want there to be exactly 2.73 microfarad capacitance from one side of the circuit to the other. For whatever reason, I don't know, you could add capacitors in series and parallel until such time that it equaled 2.73 microfarads. So for capacitors connected in series, see when I hit enter, it doesn't, I don't know. You expect the individual capacitance, the equivalent capacitance, I should say, to be, yes, in this case, less than the lowest individual capacitance. So you have a capacitance, capacitors in series that are 1, 10, and 100 microfarads respectively. Then when I add them in series, one brief mental check that you can do is that the equivalent capacitance should be less than 1 microfarad capacitance. Okay. The last thing that we need to discuss is that of a dielectric. Dielectrics change the capacitance of a capacitor by lowering the electric field magnitude within the capacitor. This in turn lowers the potential difference across the conductors. And since we're storing the same amount of charge but lowering the potential needed to store that charge, well, in that case, you would get a higher capacitance, right? So you have a parallel plate capacitor that is filled with air between the plates. Well, it turns out the dielectric constant of air is roughly 1, so it's almost the same as if you built that in a vacuum. But then you slide a sheet of plastic in between there, then you have increased the capacitance of the system, mostly because you expect that the molecules inside the dielectric, they're not free to move their charge, but their electron clouds are going to shift such that the molecules inside the dielectric polarize. And the more polarizable that the molecules are inside the dielectric is going to increase the dielectric strength, we would call it, and is going to increase the capacitance when you insert that dielectric between the plates. Specifically, linear dielectrics, which is all we're going to talk about in this class, there are nonlinear dielectrics that as you increase the external electric field, it changes the polarization inside of the dielectric. But as far as we're concerned, many different materials, at least within a small voltage range, are going to have a linear response that as you increase the external electric field, you get a linear increase in the polarization of the molecules within the dielectric, and such that we can assign a constant, a dielectric constant, where the capacitance is equal to kappa, the dielectric constant of the material inserted between the plates, times C naught, where C naught is the vacuum capacitance. Maggie? Either one. You could be solving for kappa, you could be given kappa. And you got to think too, if the capacitance is changing, then that's going to affect the energy stored. All of these different things are going to fall out from changing the capacitance. Most of the problems say, for example, I know one problem I think I've got to solve for today is you've got a capacitor, and then you slide a dielectric between it. What do you expect the voltage, the new voltage across the plates to be, assuming constant charge? Well, it gives us the dielectric constant of the thing that we slid between the plates is 2.3. And it is a unitless quantity, right? You've got capacitance here in microfarads, capacitance here in microfarads. Dielectric constant is a unitless constant that is unique to different materials. The one that 2.3 keeps coming to mind, I think that's either the dielectric constant of everyday glass, like for windows, or for plastics, like what your water bottle is made out of, but I don't remember. I only know that because we use those in the labs at Harding, so I had to know that one off the top of my head, because students were solving for it. It also means that the permittivity of the material changes as a function of the dielectric constant. Permittivity is associated with how much it, how can I say this? It's hard to say outside of an electromagnetic theory class. There's such a thing as dielectric breakdown. When an electric field gets too strong, then you expect that the charge is going to discharge. It's going to arc across two different conductors. Okay, well, if you expect a certain value with a vacuum, then that's going to increase in terms of, or you would expect the ability for arcing to increase based on the dielectric constant. So charge can arc through plastic easier than it can through a vacuum. Okay. Any other questions before we dive in? I will do my best to, if I didn't get to your question before about the exam, then maybe you can come talk to me, or come talk to me afterwards. I've got office hours after this class. Thank you again for whoever wrote hello. I reject your statement. I am a physics professor. It comes with the territory. That's a really good question. Okay, so that person said goodbye now. Thank you. Goodbye to you. Not hello. Thank you. You're like so cool. Thank you. I appreciate that. Okay. Would it be a good idea to study questions from your Menti slides? Yes. My Menti slides are a treasure trove of conceptual questions. I just sent the exams to the printer today. A few of the questions, not all 24 come from my Menti slide, but there are a few on the exam that come from my Menti slide. So yes, it's an excellent place to study conceptual questions. In series, is Q equivalent? One way to write it, let's look at it this way for equivalent capacitance for those in series. Let me scroll to the bottom of this page. So I had it written as 1 over C equivalent for those in series is equal to the sum of C sub I raised to the, or I said over 1, I think is the way that I said it. The way that I prefer to think of it as, and you'll see me solve problems this way, is I go ahead and take the inverse of both sides. So I prefer to think of it this way, where you've got C sub I inverse, taking the inverse of that. So let's say I've got C1, C2, and C3, and those are added in series. Then the equivalent capacitance is going to be equal to the inverse of 1 over C1 plus 1 over C2 plus 1 over C3. And I have to take the inverse of that, or the way that you'll see me write it out more often than not is C1 inverse plus C2 inverse plus C3 inverse. Taking the inverse of that, if each one of these is 1 microfarad, well, that would end up being equal to, or no, let's do 2, just so it's easier to see. 2 microfarad. Then that's going to be 1 over 2 plus 1 over 2 plus 1 over 2 inverse. 1 over 2 plus 1 over 2 plus 1 over 2. That's going to be equal to 3 over 2, taking the inverse. That comes out to be 2/3 microfarad, so 0.67 microfarads of capacitance. Yes. Hopefully that answers your question. If it doesn't, I'll come talk to me after class. That's the wrong, there we go. Does the kappa C naught or kappa epsilon, no. Taking kappa times C naught does not equal kappa times epsilon naught. It's just that the same dielectric can be used to scale either the permittivity or the capacitance, but it does not mean that those two equations are equal to one another. Let's see here. What was the dielectric equation? The dielectric equation was this, I think is what you're asking, either one of those two equations. If you're asking how do you solve for kappa, that's what was asked earlier. Kappa is either given to you or it's what you're going to be solving for anyway. Yes, William? Yes. Yes. Yeah, so if you think about the electric field between the that exists somewhere, it was always K times something, which is 1 over 4 pi epsilon naught, right? But you do have to consider that the electric field changes according to epsilon. So yes, because epsilon changes, you end up getting that the electric field changes as well. So if it's a vacuum field capacitor, you'd be using C naught and you'd be using epsilon naught. If it's a vacuum filled capacitor, C naught and epsilon naught. If it is not a vacuum filled, meaning that you filled it with some other dielectric, it would be epsilon and it would be C for the capacitance. Are you saying in terms of, are you saying, let's take a parallel plate capacitor, for example. We said that the capacitance for a parallel plate capacitor was epsilon naught A over D, right? Well, what we didn't know at the time is that would be for a vacuum-filled capacitor, right? But if I insert a dielectric between those plates, we said that C is equal to kappa times C naught, right? Well, C naught is this right here, so that would be kappa epsilon naught times A over D. Well, we said that this right here was equal to epsilon, the permittivity of the material. So we're still using epsilon naught, but we're also scaling everything that we've done by kappa, which means, yes, do it this way with epsilon naught or do it this way with the permittivity of the material. But epsilon naught always means vacuum permittivity. Oops, too far. Another one that got asked. That's a good question. Okay. We did that one. Kirk or Picard? That's an excellent question. I do like Jean-Luc Picard. I mean, Kirk is great, but I like Jean-Luc Picard. Why do capacitors release their charge all at once while batteries do not? Capacitors don't always release all their charge at once. They only do if you short the circuit between the capacitor plates. Then they would release their charge all at once. If there's a resistor between them, then it turns out that it doesn't release the charge all at once because the resistor is going to impede the flow, the current of the electrons. Batteries have to do with at least most of the ones that I know, some sort of chemical reaction that would take place over time as demand needs instead of shorting out all of the charge that exists there. How many questions on the exam? 24 conceptual questions, 10 numerical questions. 24 and 10. Okay, let's go on to problems here. An isolated conducting sphere, we already kind of did that one in the Menti slide, so let's do this. A parallel plate capacitor has capacitance of 2 microfarad and a plate separation of 1.6 millimeter. What is the maximum potential difference so that dielectric breakdown of air between the plates does not occur? How much charge is stored at this potential difference? And what they don't tell you, frustratingly in my opinion, on this one, is that dielectric breakdown in air and vacuum, dielectric breakdown in air happens with an electric field strength of 3 times 10 to the 6th newtons per coulomb. So that's the dielectric breakdown in air. Bless you. No. If you need dielectric breakdown on the exam, I will give it to you. What is the maximum potential difference that occurs between the plates? How much charge is stored at this potential? So how do we solve part A? How do we solve for the maximum potential difference across the plates? This comes back to Jacob's question, if you were paying attention earlier, about calculating electric field between plates of a parallel plate capacitor. Yeah, don't forget that the associated, or the additional unit that we can use here is volts per meter. So that's a really good thing to remember in terms of conceptual elements on the exam, because if you forget that E is equal, and we're just talking about magnitudes here, is dV dx. And we said that with the constant electric field, which is what we would expect between a parallel plate capacitor, that's dV dx. So if you want to find the voltage across the plates, that's going to be E times dx. So that's 3 times 10 to the 6 volts per meter times 1.6 times 10 to the minus 3 meters of separation between the plates. That gives us a maximum voltage of 4.8 times 10 to the 3 volts, or you could say that's 4.8 kilovolts. Makes me want to go back to our advanced lab at Harding where we had a 6,000 volt power supply and connect one of our lab parallel plate capacitors and see if we can start getting charged to arc across. Super dangerous. Not recommended. Do what? Yeah, in fact, it almost makes me wonder if you would end up, because the chart, it would short out so quickly and so frequently, if you'd end up melting some wires or some plates or something like that. I don't know. It's worth an experiment that I don't want to do. Watch the Kaboomer guy or whatever on YouTube who, Electroboom, yeah, I'm sure he has something like that. He loves blowing up capacitors and things like that. What? Shocking himself. Yeah. Do what? Oh, yeah. If you don't know who Electroboom is or whatever his name, so really interesting guy. How much charge is stored at this potential difference? Well, we said capacitance is Q over V. So that means Q is equal to CV. So that's 2 times 10 to the minus 6 times a voltage of 4.8 times 10 to the 3. That's equal to 9.6 times 10 to the minus 3 coulombs, or 9.6 millicoulombs. A ridiculously high amount of charge. Yeah, so we've got, this would be farads, this would be volts. And we said farads are going to be coulombs per volt. And so if I've got per volts times volts, I'm left over with coulombs here. All right. Thank you, Matthew McConaughey. A parallel plate air gap capacitor has a capacitance of 0.14 microfarad. The plates are 0.5 millimeter apart. What is the area of each plate? This only works because of this right here, parallel plate capacitor. What is the potential difference between the plates if the positive lead charge plate has charge of 3.2 microcoulomb? What is the stored energy? What is the maximum energy before dielectric breakdown? Again, that's E max is equal to 3 times 10 to the 6 volts per meter. Why don't y'all have a stab at this one, either in groups or in pairs or by yourself? Part A, you should get 7.91 meters squared, so really huge capacitor. B, you should get 22.9 volts. C, you should get 36.6 microjoules. And D, you should get 1.58 times 10 to the 5 microjoules. Or you could say that that's 3.66 times 10 to the minus 5 joules. This is 0.158 joules. Y'all have a stab at that? I'll float around and help y'all out. I know a few of y'all. I've seen them as I go around. Some of y'all have the Remarkable tablets like me. If you didn't know, they came out with a new update last night and have great new templates and all this other stuff. So if you got a Remarkable, update your tablet and get all the new templates from methods.remarkable.com. That's not a plug. I'm not being told to sell you, like I'm not selling you anything. If you're already using it, it's free. Use this link and it'll pay me 10 cents per download. Just kidding. Y'all have fun with this one. I'll float around and help you. I'll be right there. It logged me out again in the middle of class on my Google account. I'm so frustrated right now. You have? I have it open right here. I would get it if I'm don't have any active tabs anywhere, but I have active tabs. What's going on? Okay, what's up?
Sorry.
No problem. I'm mad at don't overcomplicate it. It's like a teal green. Someone check that. Oh, yeah, it looks different from Do what? Like that, the meme kid, you know? Yeah. I use a music library called AstroPi, and it's awesome because you just put in whatever you want to. You can have any SI prefix you want to, and then you're like, and now give it to me in standard SI units, or give it to me in this unit. And it's like, okay, cool. I write your exams with Python. That's how I come up with all the alternative answers. Yeah. Least favorite language? Fortran 77. Exactly. Yeah. It's an old exam. I liked MATLAB and it's when I was using it. Now I'm out of practice. Yes. What's up? Attendance? I don't know. Okay. Let's see. For the first part here, yes, what you should have had was that there is where'd it go? You've got let's see. Capacitance is equal to epsilon naught A over D. So that gives us A is equal to C times D over epsilon naught, I believe. Yep. You get the voltage across. Well, we know that C is equal to Q over V here. We know the charge, so if you want to know the voltage, Q over capacitance is voltage. You've got 1/2 CV squared for this one. The way that I would have done this one, however, would have been that the charge or the amount stored is going to be equal to 1/2 epsilon naught times E max squared times the volume between the plates, which incidentally is A times distance. So that's the easiest way to do part D without having to back solve a lot of different things. That's how I would have done that one. Man, we've only got 16 minutes left. Time flies when you're having fun. Yes, Maggie. The dielectric breakdown electric field, the max electric field strength. Okay, let's see, what else do we have here? That and that. Say that again? It will be, yes. The exam will, this is the last thing before the last new material before the exam. Yep. It is on Tuesday. Yes, the exam is on Tuesday. You confused me there for a second asking if the exam was on Monday or Wednesday. I was thinking, oh, I have something horribly wrong on our system if that's what it's listed as. Okay, if I can get y'all's attention again, we'll try to knock this out in the remaining 15 minutes. For the circuit shown, the capacitors were each discharged before being connected to the voltage source. In this case, that voltage source is this 200 volts here. Find the equivalent capacitance of both of the combination, the charge stored on each capacitor, and the voltage across each capacitor, and the energy stored on each capacitor. So this is actually a really great one to show you all the different things that you can ask from just one simple setup here. Hint, hint, clue, clue. So we want to find the equivalent capacitance of the combination. And in general, whether we're doing this with inductors, resistors, or capacitors, the latter one only that we've talked about so far, we want to see where we end up breaking down a circuit or a schematic based off of where we know the voltage drops to be. So what I'm trying to say is, if I start here, I'm going to say start here, and I want to go this way along the circuit. Well, I get to what we will call in a little bit a junction, and I have a choice to make. I can go either straight down along that first branch after the junction, or I can go to the right along that next branch. And what I want to consider here is that I get a voltage drop at each one of these different capacitors here. There's going to be a voltage drop. Let's call this one, let's see, before I just start naming them, I think I've got them named something specific in my solution. Let's call this one C1. Let's call this one C2. And let's call this one C3. And I expect here, if maybe this is useful, this is this branch here, anything that is black on the top, is going to be at 200 volts. We have a break here, so we don't know what the voltage is in here, but then anywhere along this area is all connected to the same line, so this is all at 0 volts. So the only potential that we don't know is this potential in here. We don't know what the potential between these two capacitors are. Yes, Jacob? Current doesn't go in and out. Potential doesn't go in and out. Potential is measured across things, okay? So it's not that something goes in or out. It means that the difference in energy, less charge, the difference in energy between the top and the bottom part of the circuit is 200 volts. One way that I like to think about this in terms of how do you know which things are in series or parallel, this is the most unphysics advice I can give you, but if you've ever played any of the Mario Kart games and played like DK Mountain where you go through a cannon to be fired up to the top part of this race course, right? Then that's what the power supply is. Power supply is going to be one of those magic cannons that gets you from the bottom of the track back to the top of the track. And then if it's DK Mountain, say if it's the Mario Kart 8 Deluxe DK Mountain, there are certain places on the track where you can choose to go down the left, right, or middle branches, right? That would be a junction. And things that lie on the same branch, even if there's a turn, but say if I could slide this up or down, think of them as obstacles on your DK Mountain Mario Kart 8 Deluxe track. So long as obstacles appear on the same branch, those things are going to be in series with one another. If you have to take a different branch, say if I had instead of chosen the right branch here with this lone obstacle, if I had gone down this one, then these two objects are in series with one another. The 4 microfarad and the 15 microfarad capacitor are in series with one another, whereas things that lie on different tracks are parallel to those elements. And what I'm trying to get to is, I start at a height on DK Mountain of 200 meters above the finish line. So if I start up here at 200 meters above the finish line, it doesn't matter which one of these two branches I take, I should come back down to the 0 meter line. Electrical engineers are likely cringing in their seats right now. This is the worst way to talk about it for an electrical engineer. I'm not an electrical engineer, I'm a physicist. So if this is not helpful to you, just bear with me. I'm trying to get back down to 0, and I can find many different ways to do so. But if I look at the potential drop here, it should be the same as the sum of the potential drops over here on this left branch. So before I can consider that this branch right here is in parallel to the right branch, then I have to add these two in series to one another. So what I'm going to say is C sub A is going to be the inverse of C1 inverse plus C3 inverse, taking the inverse, or that's the 1 over 4 plus 1 over 15, taking the inverse. You'll see that I'm not converting from microfarads to farads because we're just going to leave everything in microfarads. This comes out to be 3.15789 microfarads for C sub A. And what I've done now is I can redraw this circuit, the schematic, as now having a single capacitor here, C sub A, along this middle branch. And I have done nothing to touch here this C2 12 microfarad capacitor. Now I have equal voltage drop across those two things. I can now add or consider those because the voltage drop is equal across C sub A and C2. I can consider those to be in parallel with one another with nothing else involved. So the equivalent capacitance now is going to be CA plus C2 because these two things are in parallel with one another. And I end up getting that the capacitance is going to be 15.2 microfarads of equivalent capacitance in this system. So as far as the power supply is concerned, the 200 volt power supply is concerned, it just sees a 15.2 microfarad capacitor. You could take out these three capacitors in this configuration, drop in a lone 15.2 microfarad capacitor, and you would have the same circuit. Or at least as far as the power supply is concerned. Okay? Any questions on how we at least calculated the equivalent capacitance? You'll see that what I'm going to do is procedurally go to where my circuit is more and more simplified to where I can boil it down to a single individual element. And so the question then, we've gotten part A. Part B says, okay, what about the charge and voltage and energy on and across and in each capacitor? How in the world do we calculate that? You're like, I don't know. That's what I'm here for you to tell me. Yes? Yeah, okay, so let's think about it this way. The way that I tend to draw this out is I would draw a table when I'm doing these types of problems. And I've got C1, C2, and C3. And then I've got delta V, the voltage across each one of those, and the charge on each one of those. And I would write out here as a little reminder that capacitance is equal to charge over voltage, right? Well, if I look at this and start going back the opposite direction, there is 200 volts across my equivalent capacitor. That means that there has to be a 200 volt drop here. And there has to be a 200 volt drop here. The voltage drop across C sub A and C2 is the same, a 200 volt voltage drop. So I already know that for C2, that there is a 200 volt drop across that capacitor. And so what I can do then is, okay, 200 volts times a capacitance of, let's see, C2 was 12 microfarads. 200 times 12 microfarads ends up giving me, let me scroll down to my table in my notes. That comes out to be 2.4 microcoulombs of charge. Just taking the fact that Q is going to be equal to C times V. And C2, if we want to write it down, is 12 microfarads. C1 was 4 microfarads. And C3 is 15 microfarads. Okay, so we've got C2. How do we find the voltage drop across C1 and C3? How do we find the charge on each one of those? Well, what I want you to consider here is, let's imagine that according to this 200 volt drop across C sub A, it would have some charge plus Q and some charge minus Q on each one of those plates. And if that charge plus Q exists on this top branch, then that means I've got plus Q sub A here, minus Q sub A here, plus Q sub A here, and minus Q sub A here. Because we said for those in series, capacitors in series have to have the same charge. So I can find the charge, Q sub A, is going to be equal to C sub A times delta V. So that's the 200 volt drop. That gives me a charge on each one of these of 0.632, because the charge on Q sub A has to be equal to the charge on 1 and the charge on 3. So now I know how much charge is on each one of those capacitors here in this left branch. Capacitors in series carry the same charge. So how do I calculate the capacitance on, the voltage drop across each capacitor? Yeah, go back to this original equation. We can rearrange it such that V is equal to Q over C, taking this charge and dividing it by this capacitance. For C1, you end up getting a 158 volt drop across C1, and you end up getting a voltage drop of 42.1 volts across C3. Now, one thing you want to consider is, we said if you're playing Mario Kart Deluxe 8 and you have a 200 volt drop from the top to the bottom, then we'd expect that the voltage drop across the first plus the voltage drop across the second, 158 plus 42 volts, equals my total voltage drop of 200 volts across those two things combined. And if you want to calculate it as an additional element here, you could calculate the charge stored. Just take 1/2 CV squared, and just for you guys, this would come out to be 49.9, and this is going to be in millijoules. You would get 240 millijoules, and you would get 13.3 millijoules. So the largest capacitor does not necessarily have the most energy stored on it. It could if they were all in parallel, but in this case it doesn't. Y'all have a great day. Okay.